All right, recording has started. Okay. I see that at least some of you have taken the test already, and you have until Friday night to do that. So after the due time for the test has passed, then over weekend I will be examining the tests in case there needs to be any um, credit given. Actually, one thing I want to check here about the test. Okay. Oh, okay. Because people have already taken it, it won't let me. I want to actually pull up the problems, not to show you, but just on my screen. Okay. So let me check the chat. 1 hour and 15 minutes is the time limit. So it's the same as a class period. Okay. Oh, okay. Shoot. All right. I just realized that one thing I meant to do when composing the test, because what it does when you create an assignment, by default, each problem is worth 1 point. So that's what you have on this test. So what I'm going to have to do is when I examine the test, like let's suppose I look at a problem that you got the wrong answer for, and I want to assign partial credit, but that wouldn't work for 1 point. So what I'll do is I'll have to basically manually figure out, okay, here's how much credit you should get for this problem, and convert that to a percentage, and then I will override your score with that percentage. So as an example, let's suppose you take the test. There's 6 problems on it. You get 5 of them right. So your score is 83.333%. So then I look at it after and I see that on the one problem that you got wrong, like so let's suppose it was a multi-part answer or something, and I think that you should get half credit for that problem. So then what I would do is your percentage therefore would be, you know, the 83.3 that you got plus half credit for that problem would add on another 8 points or so. So then your score would be about 92%. So that is what I would enter into the grade book. So right now, because each problem is 1 point, you get it wrong, it's like an all or nothing kind of deal. But to the extent possible, based on what I would see, I would see if there's a possibility of partial credit. So I will do all that over a weekend, so that by Monday, hopefully, not promising anything, but it's going to be a busy weekend. But that's what my goal is for Monday, for your final score to be known. And I want to thank those of you who have gotten 100 on the test. and therefore in that case there's nothing to review. Okay, so just keep it in mind when you take it and see your score. The score might increase. All right. Okay. But yeah, I goofed there. I meant to go into edit a test and assign point values to all the problems that would add up to 100. And unfortunately, I forgot to do that. So it's something I will do. Yes, 6 questions. Yeah. So the weight is now at 6 questions worth 1 point each. But I'll be working with percentages in the grade book. Okay. Yes, when I made the question similar to a practice test, when I made up the real test, I literally made a copy of it and called that to practice test. Obviously, certain minor details changed about the problems, but that's exactly what I did. Okay. Now, we're probably not going to have a very long class today, just because what I have in my schedule is to start covering the next material, which is section 2.1. So we're getting a new chapter on matrix operations. And I've already made up a homework for that section 2.1. It's not due until next week, like October 1st, specifically, so a week from tomorrow. So I'm going to start covering that section today, and then I will finish it on Monday. But so there's not a whole lot of material each day, but I'll go through the first 5 problems today and then finish that on Monday. All right. So then if you've finished the test already, then you can go ahead and jump into that homework. Actually, I want to see if I look in the grades. Okay, yeah, there are 36 people in the class, and 7 people have taken the test so far. But there's still plenty of time. Okay. So here we're going to be dealing with certain fundamental operations on matrices. And since we've been working with matrices already, just learning matrix arithmetic. So that means adding, subtracting, multiplying matrices, not dividing. We'll come to something like that later. Also, scalar multiplication of matrices. So multiplying a matrix by a number. So these are kind of operations we'll be dealing with now that'll be useful in a variety of linear algebra problems. So what I want to begin with is a formal definition of matrix addition, matrix multiplication, and these definitions are motivated by linear transformations, because we've seen if you have a linear transformation from one vector space to another, like from Rn to Rm, any linear transformation is associated with its standard matrix. So operations on linear transformations can be described in terms of their standard matrices. So for addition, the more straightforward operation, we have 2 linear transformations, and notice the domain and range are the same. So they both take n inputs and give m outputs. So these 2 linear transformations therefore would have 2 standard matrices, which I'll call A and B. So then if I define a new transformation, that's just the sum of the 2 given ones. Then what's the standard matrix of T? Well, that's just taking a standard matrices of these transformations and adding them. And the adding and subtracting matrices, very straightforward, unlike multiplication. So the sum of a matrix, all we're doing is we're adding up corresponding entries. So we just do an entry by entry addition or subtraction, as the case may be, and that's all there is to that. Multiplying a matrix by a number, also very straightforward. Like if I have 2 times A, that just means I'm multiplying all the entries of A by 2. So those are two of the matrix operations that we'll be dealing with. But the other one, definitely more of a pain, and that is matrix multiplication. And that comes from a different combination of linear transformations, composition. So here I have different transformations of different spaces. So R takes in n inputs, has m outputs, whereas S takes in p inputs, has n outputs. So the number of outputs of this transformation is the same as the number of inputs of this transformation. So what is possible to do then is to chain them together. So I define a new transformation T where the number of inputs matches S and the number of outputs matches those of R. So what do? It's a composition. So you apply S to X first, and then you take the result and you plug it into R. So it's a function of a function situation. Like from calculus, you dealt with compositions of functions, and you had to take the derivative, and you would need a chain rule for that. So it's the same kind of idea here. So in this case, if I want to work out the standard matrix of T, given the standard matrices for R and S, how would you do that? Now, I won't show like algebraic manipulations involved to figure out standard matrix of T from these two, but I can tell you the formula for it. It's the matrix product. So I multiply the matrices A and B, and that gives me the matrix C. So the matrix of a composition of linear transformations is the product of the standard matrices of those transformations. So how do you multiply matrices? It's a very tedious process. Notice here I'm describing one entry of a product. So it's not like addition where you can just add corresponding entries. So we're not multiplying corresponding entries here. But notice there's a summation involved, and from this formula, it's difficult to have an intuitive understanding of what how to carry out the matrix product. But I will be able to show you that in examples. But if you might remember from calculus, the dot product is an operation that you would have seen in Cal 3, where you're learning how to work with vectors. So if you have two vectors of the same length, same dimension, to obtain the dot product, you multiply corresponding components, and then you add them all up. So it's easier to understand matrix multiplication in terms of a dot product. Now we're taking a row of the first matrix A, dot product with a certain column of the matrix B, and you're doing all possible dot products of rows of A with columns of B, and those give you individual entries of the product. So what I will do in various problems are illustrate all of these operations, and then then you'll be able to see like, okay, how do you carry out matrix multiplication like on paper? Okay. So in fact, all of the operations I want to talk about today are illustrated in this first problem, but we'll see other ones too. So here, given 4 matrices A, B, C, D, and the task is to carry out these 4 operations on these matrices. So I'll just step through them one at a time. Okay. Okay. So the first one, all we're doing is we're taking this first matrix A and we're multiplying it by -3. So all that means is we're taking each individual entry of A, multiplying that entry by -3. So not much going on here. So we just carry out the product of each entry and then we're done. Then I'm going to use that in this next operation. So here I have B added to -3A. So for that operation, okay. So first I'll throw in B. Okay. And then now here we have B plus the matrix -3A, but that's what was computed from the last part. So so really what I'm doing is I'm just adding these matrices together, and we see that we're just adding corresponding entries. So 7 plus -9 is -2. -4 plus 0 is -4. And we can just keep, and we do that for all of the entries. -2 and a -6 gives us a -8. So it's just component-wise or entry-wise arithmetic in these first two cases anyway. Right. Now, the next operation that's called for is A times C. Now, when you're multiplying A times C, the matrix multiplication operation is not always defined for any two matrices that you have. What's required is that the number of columns in the first matrix, so A, must be equal to the number of rows in the second matrix, in this case C. So here A has 3 columns, but C has 2 rows. So this operation actually does not make sense. The opposite, if I did C times A, C has 2 columns and A has 2 rows. So C times A is possible, but A times C is not. So those dimensions, so the number of rows of A or columns of C, that has no impact on whether the operation is defined or not. That just determines the size of the result. Okay. But if we look at C times D, C has 2 columns, D has 2 rows. So that operation is defined. Okay, so if I show you C times D, okay. All right, so here I've just placed them here. So now to carry out the product, so I do this one entry at a time, and I'll show you what operations that actually entails. So first, I'm going to go across the first row and down the first column. And you're multiplying corresponding entries. So I have 2 times 4 plus 3 times -1. So again, go across the row, down the column. And because it's the first row here and first column here, all of that goes into the 1, 1 entry here. Similar for the entry in row 1, column 2. So row 1, column 2 deals with the first row of C, second column of D. So I have 2 times 4 plus 3 times 4. And that gives me the 1, 2 entry. And so this is an illustration of what I wrote up above. So let's go back to that real quick. So if I want the entry in row I, column J of a product, then it comes from row I of a first matrix, column J of the second matrix. That's how we get each of these entries of a product one by one. To get the second row of a product, I need to use the second row of the first matrix, C. So here is entry row 2, column 1. So the 2, 1 entry. So I use the second row of the first matrix, first column of the second matrix. So I have minus 2 times 4 plus 2 times minus 1 down here. And then for the last entry, row 2, column 2. So I use the second row of C, second column of D. So I have minus 2 times 4 plus 2 times 4. So these are how all the entries of a product are set up. So then I go ahead and actually work those out. And here's our product. Now, this is only the first example of matrix multiplication. There will be more. But are there any questions at this point about how the operation is carried out? Now, these next problems don't deal with matrix multiplication, but scalar multiplication involving matrices, and also addition and subtraction. And here we have a matrix that I've showed you once before, the identity matrix. So what's asked for is twice the identity matrix minus A. And then here we have matrix multiplication, but of a very simple kind, 2 times the identity matrix, and you multiply that by A. Okay, so our first operation, 2i, 2 times identity minus A. Now, in case you've forgotten, the identity matrix is a matrix that has ones down the main diagonal. So from upper left to lower right, you have ones. All other entries are 0. So that's the identity element for matrix multiplication. So I'm multiplying that by 2, and then I'm subtracting off A. Now, when you are multiplying a matrix by a number, you're just multiplying every entry by that number. So 2 times the identity would just give me 2 on the diagonal, 0s otherwise. Okay. So then all that's left is just to subtract off A, but that's just going to be component-wise subtraction. And it's only going to affect the diagonal entries because the off-diagonal entries here are 0. Okay. So here we see the component-wise. Oh, you know what? I just realized I goofed on the off-diagonal entries. So we have A is being subtracted. Sorry about that. So minus a minus 2, and then same here we have a minus 6, and then we have you know what? I went the wrong way. So Okay. All right, so here I'm just subtracting corresponding entries. Okay. All right. So then once we carry that out, okay. So then here's the final result. I think I'm so accustomed to subtracting multiples of identity from matrices that out of habit I just kept doing that. Okay. All right. Now, the other operation is 2 times the identity multiplied by A. Now, here we have identity matrix again multiplied by 2, and all of that is multiplied by A. So then here we carry out the multiplication by the scalar 2. So that's just, we saw this before, 2, 0, 0, 2. Just multiplying every entry of this by 2 times A. But there's actually no need to carry out the full process of matrix multiplication when it's just a multiple of identity, because identity times any matrix is that matrix. So identity times A is just A. So really, all that's needed is just to take A and multiply it by 2. So equivalently, matrix multiplication, I should mention, is not commutative. So if I have two matrices A and B, even if multiplying them makes sense, A times B does not equal B times A. Be very careful about that. Again, matrix multiplication, not commutative, but it is associative. So here we have this product. I can write it this way, 2 times, I can compute the product identity times A first, but identity times any matrix is just that matrix. So really that's all I would need to do in this case is just take the entries of A multiplied by 2. Okay. So that's one simplification that you can make. The next problem has the same kind of operations, just on a 3 by 3 matrix instead. So if I look at A, this A minus 5 times the identity. All right. So here I have a 3 by 3 identity matrix. Again, 1's down a diagonal, 0's elsewhere. But that's multiplied by 5. So then I just go ahead and carry out that scalar multiplication. Okay, so now I have 5's down a diagonal. And then all I'm having to do is just subtract 5 from all the diagonal entries. So this is the main diagonal. I'm going to subtract 5 from each entry there. Everything else is left alone. So then I go ahead and carry out this arithmetic for every diagonal entry, and get the final result there. And then, based on the last problem, if I want to do 5 times the identity times A, all I would really need to do is, since identity simplifies, identity times A is just A. So really, I could just take the entries of A and multiply them by 5. Not sure why it's formatted that way. Oh, I see what I did. Okay. Yeah, so here we have A here. So just multiplying every entry by 5 gives us a result. Now, one thing I want to point out, though, is if you look at the steps in full, even though there's a quicker way to jump to the results. Well, first I'm going to put this on a new page. Okay, so we have 5 times the identity times A. And then working out 5 times identity. Okay. Now, a matrix like this that has it's only non-zero entries on the main diagonal that I'm highlighting here. It's actually very easy to multiply a matrix by this kind of a matrix like A by a diagonal matrix such as this. Again, you don't have to carry out the full entry by entry process that I defined earlier because of this simple rule that you can follow. So here I'm taking A and multiplying it on the left by a diagonal matrix. So the only non-zero entries are here in a diagonal. And how does that work? What you do is, if you're multiplying on the left, then you're scaling every row of this matrix by the entries here. So in this case, they're all equal to 5. So I'm scaling every row by 5. Whereas if these were different numbers, like suppose I had 5, 4, 3, then I'd multiply the first row by 5, second row by 4, third row by 3. So that's what happens when you multiply by a diagonal matrix on the left. But if I take this matrix A and multiply it by a diagonal matrix on the right, then I'm scaling columns. So if I put this matrix over here, I'd be scaling every column by 5, and the end result is the same. That's because all these numbers are the same. But so that's a shortcut for you. If you ever have to multiply 2 matrices and one of them is a diagonal matrix like this, then it's just a matter of scaling rows or columns. So scaling rows if a diagonal matrix is on the left, scaling columns if the diagonal matrix is on the right. So save yourself some time. Okay. All right. So here we have 2 matrices to multiply. So it's featured in the next 2 problems. And what you can do is you can work them out one column at a time using an operation that we've seen already. That's a matrix vector product. So what you could do is if I write B in terms of its columns, all right, so I have, whoops, B1, B2. So here, these are the two column vectors of B. Then the product A times B can be obtained this way. So all I got to do is take each of those columns, B1 and B2, and multiplying on the left by A. So any matrix product is really just a juxtaposition of matrix vector products, which were seen in the previous chapter. So what I can do is, if I want to multiply these two matrices, I can compute the product of them one column at a time. So I focus on AB1, then I do AB2. So in this case, I'll start with AB1. So there's A, and there's B1, the first column, the 5 to the minus 2, first column of B. So then what I can do is, there's a couple of different ways of looking at this. I can go across this row and down this column to get the first element, and then cross this second row down this one column to get the second element, and then using a third row and its column to get the third element. So written out in full, so minus 2 times 5 plus 3 times minus 2, similar for this one, and then 5 times 5, and then plus minus 4 times minus 2 for the third element. So we go ahead and carry all that out. But I want to show you another point of view that you might prefer. How we viewed matrix vector multiplication in the previous chapter, where you take each column of A and scale it by the corresponding element of vector B1. So this is the same as if I take the first column of A, so minus 2 to 5, okay, times the first element of B1, so that's 5, and then the second column of A times second element of B1. Okay. So then you can work it out this way and just like you scale these column vectors and add them up. All right, so I have okay. So in this case, I have minus 10, 10, 25 from this first term. And then here we have -6, and 8. Right. And then you can go ahead and add these up to get this same result. Okay. All right. So what we have here, however you get it, this is the first column of a product A times B. So then all we have to do is repeat the process with the second column of B. And I have that detailed out here. So AB2. So we have A again, second column of B. So we see that the operations to be carried out. So again, going across each row of A, and then down this one column, the only column we have here, multiplying corresponding entries and adding them up. So -2 times -1 plus 3 times 3 to get the first element, and then going across this row and this column to get the second element. So 2 times -1 plus 3 times 3, and then finally down here, 5 times -1 plus -4 times 3 for the third element. And this is our result. And so that's the second column of a product AB. So then all you have to do is slap those two columns together. Okay. So AB1, AB2. All right. So questions on this approach to matrix multiplication. All right. Here we have another. All right, so here we're working with to compute AB1. So we're dealing with the first column of B right here. So so if I were to fill this in, all right. So without actually carrying out the operation in full, but just understanding what numbers are used when. What would I actually be multiplying and then adding up? Like if I want to get the first entry of this product. So for this matrix, this column, and I want the first element of a result. What am I actually multiplying and then adding here? based on what I did the last one. Or you can type it out in the chat if you want. That's in other words, like the numbers that I needed to put together here to get these results. What would I have in place of this for this example? Anyone? Okay, I see something in the chat here. Okay. Yes. -2 times 3 plus 2 times -2. All right, so we have it for the first entry. Okay. And then the process is the same for second and third entries. So it's still going to have 3 and -2 here and here in these spots. What goes in these spots are the entries from whatever row you're working on. So for a second element, you have 3 times 3 plus 3 times -2. And then similar for the third entry. So that's how you put all the different numbers together to get the elements of a result. Very good. So then we get the first column of the product AB here. And then the process is repeated for the second column. Whoops. Okay. So same thing, same matrix, but then the second column of B is what goes here. But notice that the second column of B is just the negation of a first. So in this case, we're just going to get the negative of this vector for the result. Okay. Okay. All right, so then we have the columns of results here just by putting those two together. Okay. Now, are there any questions at this point? Okay. I do have more problems from this section, but those I'm going to defer to Monday. So I will end the recording at this point. Anyone who has any questions can stick around.